I'm Iz.
And I'm Sid, and we're the Science Kids, and we are going to teach you all about physics today. All right, let's jump right into it. Izzy, what's work and what is power?
Well, work is the distance you exert force on an object, and power is the rate at which you do work.
Here's an example of work. If I push this pool floaty 10 meters, which is the distance, with 10 newtons, which is the force, then the work will be 100 because you multiply them together. This is calculated in joules.
If I push it for 5 seconds, you would divide the work, which is 100 joules, by 5 seconds, which is the time, and you would get a power of 20 watts.
An example of kinetic energy is rolling a bouncy ball. How to calculate this is mass times velocity squared.
Potential energy is energy due to height, as if I were to drop this basketball. And it is calculated by multiplying the mass times the height by gravity, which is 9.8 meters per second. Surprise! We're on a roller coaster!
We're at the top of the roller coaster. That means we have a lot of potential energy.
Woo!
Because we are at a big height.
Now that we're in motion, we have a lot of kinetic energy, which is energy due to motion.
However, as we move closer to the end of the roller coaster, we are getting more and more dissipated energy, which means this is the energy lost due to friction of the track, for example.
So, say that both the donut and the pizza were neutrally charged objects. If they rub together, the transferring of electrons or protons could occur. Say the donut gave 1 proton to the pizza, then the pizza would become positively charged and the donut would become negatively charged.
Say we were both positive charges, we would repel each other. Say I was negative and she was positive, then we would attract. Welcome to Sid and Izzy in the kitchen.
Today we're going to show you some conductors and insulators.
A wooden spoon is a perfect example of an insulator. This is because when cooking, it doesn't allow heat to pass through it.
On the other hand, we have a metal pan. The metal pan is also good for cooking because it's a conductor. So the heat from the flame can go up through the metal, which is also why it gets really hot when cooking. And you're trying to find the resistance when the current is 0.6 amps. So, to do this problem, you would use the equation resistance equals velocity divided by the current. Since you're trying to find resistance, you can plug in the velocity, which is 12, and the current, which is 0.6. Solving that, you would get that the resistance equals 20, which is measured in ohms. So there you have your answer, which is 20 ohms, and that is how you use Ohm's law.
Again, we're going to use this diagram to find electrical power, which is the power used in an electric circuit. So to find this, we'll multiply the volts times the current. So that's power. Volt is 12 times the current, which is 0.6. Then you multiply the two together, and you'll find that the power is 7.2 watts.
I'm a series circuit.
And I'm a parallel circuit.
In a series circuit, there's only one loop and path to flow through. Meaning that this is a relatively simple circuit. The current is the same throughout. And in this one, if one light goes out, all lights go out. In addition, a series circuit looks kind of like this.
Now let's move on to parallel circuits. In this one, whereas in series there's one loop, in parallel there's multiple loops. Also, it is bigger and more complex, unlike this simple series circuit. The current is not the same throughout. And if one light goes out, others stay shining. Example of a parallel circuit looks like this. Instead of all the lights on one, there'd be multiple sections. So, for example, a light is here and a light is here. They don't affect each other.
Electrical storms! During an electrical storm, your first priority would be to get inside. If you're outside and you want to stay away from tall items such as posts, poles, or trees, because those can conduct electricity. Avoid metal and water, for these are also conductors of electricity. If you are outside, uncovered, and there is lightning, you want to stand with your feet close together, not spread apart, because when they're close together, the electrical field lines are also, you are on the same electrical field line, meaning that there is little potential difference and therefore you will not get shocked by the lightning.
And if you can, go inside a car. This is because it can shield you from any lightning. The car is absorbing all energy, keeping you safe.
Now for some lessons on transverse and longitudinal waves. An example of a transverse wave is an ocean wave because the motion of the wave is perpendicular to the direction it is traveling in.
A longitudinal wave moves parallel to its direction it's traveling in. And an example of this is a sound wave. Izzy!
Transverse waves. Transverse wave looks like this and has a few important parts. This is the crest of the wave, which is the highest point. The trough is the lowest point of a wave. From one crest to another crest, or one trough to another, is considered a wavelength and is marked like that. The resting position of the wave goes through the middle of the wave. And the amplitude of a wave is measured from the resting point to the crest, or the resting point to the trough.
So now we're going to move on to a longitudinal wave. An example of these are sound waves, remember? So this is what they look like. So the resting position would be the same. Then there's the amplitude, which is the maximum extent of vibrations or oscillations measured from the position of the equilibrium, which is this. So this is amp. Then we have the wavelength, which is from like a crest to a crest. Remember, that's our symbol for wavelength. Then we have a compression, which is the region where the particles are closest together. So this is the compression. And then we have the region where the particles are closest or farthest apart, where this is the rarefaction. So there you have.
Now, what would happen if you tried to find the speed of sound at a certain temperature, because the speed of sound changes depending on the temperature outside. So the velocity would be 331 meters per second, which is the speed of sound at 0 degrees Celsius, plus 0.6 times the temperature that it is outside, which would be 20 degrees Celsius. 331 plus 0.6 out of 20 is 12. And when you add them together, you get 343 meters per second.
So now we're going to try out a problem and find wavelength. Wavelength, this is the symbol for wavelength, is equal to velocity divided by frequency. We're going to take our velocity we have from our last problem, 343, and then divide it by, let's say the frequency is 10. 343 divided by 10, the wavelength would equal 34.3. Then we're going to look to our electromagnetic spectrum and see which category it falls into. This one would fall into a radio wave because it fits in the spectrum of 10 and 10 to the third. 34 fits into this spectrum, meaning that the wavelength would be a radio wave.
In standing waves, nodes, antinodes, and resonance all play a part. For example, resonance is when the frequency of force vibrations match the object's natural frequency, which is how we get standing waves like these. However, it also relates to the nodes and antinodes. For example, the center is a node where it looks like there's almost no movement, where these spots here are the antinodes where you can definitely see movement, and those are created with that resonance.
For example, I'm going to teach you about constructive interference and destructive interference of a wave. Constructive interference would be if we both sent a wave and the wave became bigger from the two. Destructive interference would be if we both sent a wave and that negatively impacted both the waves and made them smaller.
The amplitude of sound waves is measured in decibels. For example, if you yell really loud, it would be a higher number of decibels than if you were to whisper really quietly.
The Doppler effect is the apparent change in frequency of the wave due to the motion of the source or of the receiver. That's a perfect example of the Doppler.
Sound waves can also reflect, refract, or be absorbed. In reflection, the sound wave travels to a barrier and then bounces back in the exact same direction that it came from. In refraction, the sound wave bounces, and once it hits the barrier, bounces back in a different direction. In absorption, however, the wave hits a barrier and is absorbed by the barrier, sometimes completely or sometimes part of the wave is then reflected or refracted.